Hello students, continuing with quantum statistics. In the previous lecture, we discussed in detail the black body concepts and Planck's law of radiation. In this lecture today, we will show you the approximate cases where Planck's law hold good for short wavelength and long wavelength. Now, your favorite examination question is prove that for short wavelength, the black body radiation is obeying the Wein's radiation law and that it is a special case of Planck's law of radiation. We should keep one thing in mind that Planck's law reduces to Wein's law for shorter wavelengths, not for the longer ones. So Planck's law for black body radiation states that E lambda is equal to 8 pi hc lambda to the power of -5 upon e to the power of hc divided by lambda kt minus 1. Now, have a closer look at the expression. For short wavelengths we are talking about. So this expression is becoming very large compared to 1. So what we are going to do for a very large number, if you subtract 1 from it, it makes not much of a difference. So you will neglect this -1 and your expression reduces to E lambda equal to 8 pi hc lambda to the power of -5 divided by e to the power of hc lambda kt. And now what we will do, see 8 pi hc, they are all constants. 8 is a numeric constant, pi 3.14, h Planck's constant, c velocity of light. So we will assume it as capital A and small a to minus hc by k, and then the expression reduces to E lambda d lambda equal to a, which is a constant, lambda to the power of -5 e to the power of minus a upon lambda t into d lambda. This formula is true for short wavelengths only. Hence, Wein's law can be derived from Planck's law as a special case. Now, for long wavelengths, the black body radiation obeys Rayleigh-Jeans formula, that is E lambda d lambda equal to 8 pi kt upon lambda to the power of 4 d lambda. And also again, it is a special case of Planck's law of radiation. So again, remember, this is applicable only for long wavelengths. So Planck's law for black body radiation is E lambda equal to 8 pi hc lambda to the power of -5 upon e to the power of hc lambda kt minus 1. Now, this is for very long wavelengths. Hence, hc upon lambda kt becomes less than 1 and e to the power of hc by lambda kt is equal to 1 plus hc by lambda kt approximately. And then this expression reduces to E lambda d lambda equal to 8 pi kt upon lambda to the power of 4 into d lambda. So this is correct for long wavelengths only. Now, derive Wein's displacement law as applied to black body radiation from Planck's law. Wein's displacement law states that as the temperature of a body is raised, the maximum intensity of radiation emitted by it is displaced towards shorter wavelength side. That means lambda m, that means the maximum wavelength into T is a constant, and deriving it from Planck's law, we know that Planck's law of radiation is E lambda equal to 8 pi hc lambda to the power of -5 upon e to the power of hc lambda kt minus 1. Differentiating the above law and equating it to 0, what do we get? dE lambda upon d lambda equal to 8 pi hc into d by d lambda into lambda to the power of -5 divided by e to the power of hc lambda kt minus 1. Now, we will be differentiating this expression with respect to lambda. We will use the formula d by dx of x to the power of n is equal to n x to the power of n minus 1. And once we differentiate this expression, we get the equation in a very simple form where ex into 1 minus x by 5 equal to 1. Here x is hc upon lambda kt. This expression will have two roots and we will simplify both the roots. We get the value of the constant lambda t equal to 2.898 into 10 to the power of -3. And this is a constant which is known as Wein's constant. So Wein's displacement law becomes lambda m into t is a constant which is known as Wein's constant. Now numericals will be there in the next lecture series.